Hey, so the first problem set was just due. Hopefully you all did it. The second problem set, which is up there, is due, I believe it's next Friday because there's no class next Wednesday. So it's due on the 21st at class time. And it's about bowling. It's about, much of it is about things rolling around or sliding around. So it's about rotation, it's about friction, and you'll see it's a few other things in there. I guess if you've got questions about this first problem set, come and talk to me. Alternatively, you can ask them live or on text. Anything you want to talk about with regard to the first problem set? Questions you have? Otherwise, just trying to keep moving along a little here, I'm going to go on to seesaws. So start seesaws. We'll see what happens Friday given the weather. Okay, anyway, but back to seesaws. I'll try to keep my focus here. So seesaws, we'll see, is the story of rotational motion. So I've talked a lot about going somewhere, moving, things moving. The escalator problem, for example, the problem set is about going somewhere. And seesaws is not going, ultimately you're not going anywhere, you're just turning. And so I've tried over the years, various topics as this way of looking at rotation. I did wind turbines for a while, but seesaws ultimately is easier to work with. So let me start off and see to what extent you all have looked at the book or my lecture videos. And so I'll ask you a question to start off here. And that is, in which direction is my angular velocity? And I have to move in order for this to work. So let me get this guy started here, and then I'm going to show you what I'm talking about. So here I go. Ready? Okay. So in which direction is my angular velocity when I'm doing this? I should have put on F. Huh? Okay. Anyway, you okay with the question? What direction of my angular velocity? Let's see what you got. I'll give you another 10 seconds on it. It's a question you can either do or not do. 5, 4, 3, 2, 1. Well, 41% of you got it. It's the purple one. It's D, downward. The fact that it's at that level means I should spend a minute or two or more on these. The world of rotation. Up until now, I've talked about translation, where you're going somewhere. So, for example, right now I'm translating. I'm moving. You know, maybe it's physics jargon, but it's just so entrenched that it comes off my tongue pretty easily. This is translational motion. I'm going somewhere. I have a velocity. It's not zero. I'm heading off here to the left. The world of rotation is, in many ways, analogous to the world of translation, but you don't go anywhere. You change orientation. It's all about orienting differently. So, for example, right now, I'm not going anywhere overall, but I'm moving. The movement's a different kind. It's rotational motion. And there are 5 physical quantities worth thinking about that we'll use and talk about rotational motion. We won't deal with rotational motion nearly as much as translational motion over the rest of the semester, but it's worth seeing it and realizing it's there. You do use rotational motion often enough. I don't want to completely neglect it. So the 5 physical quantities of rotational motion, analogous to the ones of translational motion, are, first off, angular position, which way something is oriented. So if right now I'm oriented facing you guys, we can call this angular position 0. This is the start of anything. And if I orient myself differently, I have an angular position that's not 0. And it's not 0 both in an amount and in a direction. The direction is the complicated part. It's not too surprising that this is 0, And this is 90 degrees. I mean, I did this on the lecture video. It's not surprising that we would call this 90 degrees. Or basically, you can use any unit of angles. 90 degrees is probably the one you're most familiar with. There are other ways in which to measure angles. In particular, is the mathematical, sort of a fundamental way of describing angles in terms of what are known as radians. Do I care whether you understand radians? Not really. But so this is 90 degrees. Questions about this being 90 degrees? You okay with that? The issue is, it's 90 degrees, but so is this, so is this. They're all 90 degrees away from the original, from the zero. But they differ in the way in which I rotated to get there. And this particular rotation is most easily described in terms of a direction. And the direction is along the vertical axis, because that's sort of the rotisserie axis about which I had to be rotated to get to this. So to go from there to there, I spun about an axis that was vertical. To go from there to there, I spun about an axis that was horizontal like this. So scientists and engineers have sort of forever described angular positions that are different from the origin in terms of how far you rotate away from the origin, from the zero, and about what axis you rotate. We're okay so far? I'll come back. I'll come back to that question. All that remains, though, is the ambiguity between this rotation of 90 degrees about a vertical axis and this rotation of 90 degrees about a vertical axis. They're both 90-degree rotations, but they're different. I end up in a different angular position. And the convention has been to observe that the rotational axis, this vertical one, has two directions along it, up and down. And we'll name one of these rotations up and one of them down. Actually, I had it back. That's actually backwards by bad chance. The convention, any convention would do, the convention that has developed over the years is to describe this one as downward and this one as upward. And how in the world would you ever remember that? Well, you use your right hand. It's one of a number of right-hand rules. And the right-hand rule is this. You take your fingers and you curve them in the direction in which the turn occurred. And I hope you can sort of visualize that if I go like this, that's the curve with my right hand. Is that okay? My surface is going that way as opposed to that way, okay? This way. My thumb points in the official direction. Thumb of your right hand. It's got to be your right hand. The world, just as an aside, the world has certain aspects in which it's symmetric, and it's very hard. You cannot tell somebody where I want to go with this. Background. We're using an artifact that you know from childhood. You know which is your right hand. I mean, presumably, there's surely some people who have sort of a dyslexia and can't get it. But you know which is your right hand. It's an artifact you were born with. And we're using that artifact to distinguish down, thumb down, from up. Because on a telephone, you couldn't tell somebody which is which without them also having an artifact. If you called them up and said, I rotated 90 degrees about a vertical axis, they would, so I was facing the straight ahead, and now I'm 90 degrees away, and you're on the phone with them. They'll go, well, okay, you're either facing to what used to be your right or what used to be your left, but I can't tell which. And can you give me more information? Well, without referring to an artifact of some sort, you can't do it. You can't tell them. When you refer to right or left, you're actually referring to an artifact that you have built in your memory. You know which is your right hand, and therefore which is right. And you know which is left. If you're not allowed to use things that you remember because you were taught them, you can't tell them over the phone which it is. There is no way to distinguish this from this. You have to have something that you all share as an artifact, either in your mind or physically. Which is your right shoe, which is your left shoe. You can't tell them apart over the phone. You need an artifact. You need to remember which is right. Anyway, I'm off on a tangent as usual. So this is down. This is up. You okay with that idea? And why is this downward? It's because we have the two directions along the vertical axis, upward and downward. We have to choose one, choose the other. This, by convention, has been called downward. It's just a choice. It turns out not to matter what the choice is. You could have another civilization somewhere far off where they would have called this one down, up instead of down. It's arbitrary. You just got to stick with it. Once you stick with it, you're good. And to remember the convention, which I will never test you on, so you can like zone out now, we use our right hands. That's all. I don't really want to make a super big deal about it. Okay. So angular position, we can now describe orientations using an angle and a direction of rotation. And therefore, it's a vector quantity. It's a vector quantity where what's up about doing this? It doesn't seem any up at all. It all seems to be taking place horizontally. It works. It turns out to be a useful way of identifying this angular position. That the fact that there's no upward movement or something like that, don't worry about it. It's about distinguishing more than it is, and identifying more than it is about seeing which way things are moving. Angular position is relatively less useful than angular velocity. Things spin a lot. You don't really care about which way they're oriented right now, but you do care about how they're spinning. So right now I've got an angular velocity. It follows the same kind of rule in terms of direction. I'm turning about a quarter of a turn per second, which is a perfectly good way of quantifying how fast I'm turning. This is about a quarter of a turn a second, or it could be 90 degrees per second, or it could be pi over 2 radians per second. They're all the same. The only issue left is the direction of the turning. Well, again, it's about a vertical axis, and using the right-hand rule, I'm turning downward. And that's the question that was up here, which I asked you. You're turning downward because I'm turning downward. My angular velocity is about a vertical axis. According to the right-hand rule, it's the downward choice. This would be the upward choice. Okay? The question that came up here is, when it's raining, do you get wetter if you walk or if you run? And the answer, it's a classic question, and the answer is go as fast as you possibly can, because you are going to, when the raindrops coming down, the amount that hit your top depends on how long you're exposed to them. So with every passing minute, you're going to get a certain amount of rain hitting the top of you. The rain that hits the front of you simply depends on the volume of space that you occupy between the start and the finish. You sweep out a chunk of space going through there, a human-shaped spaghetti, piece of spaghetti. And all the water that's within, all the drops that are within that, at any average moment, you're going to wear them on your front. Whether you go slow or whether you go fast, it's just a question of how fast you pick them up. You're going to get them all. And so that's fixed. Whether you walk or run, you're going to hit the same amount with your front. What remains, though, is what hits you on the top, and that's completely time-dependent. Go fast. You don't get as wet. Is that okay? That's the physicist's take on it, and the details of whether you're moving more like this. That's complication. Any questions about that idea? One of my hopes with this class is sort of problem solving, that you learn problem solving. And so what's the physics in that story? Not much, but there's a lot of problem solving in it. So when they ask you this at your interview for some consultancy, you know how to think it through, right? Okay, Oh, so it's a question about Atlas holding the world, which I think I've seen in political cartoons lately. Atlas holding the world up. Doing work, no, not doing work. If Atlas simply holds the world, I don't know, on his shoulders and nobody's moving, how much work does Atlas do? 0. This, of course, assumes that the Earth weighs anything on the surface that Atlas is standing on, presumably a bigger planet. So it's kind of messy. Actually, I can be Atlas right now. I'm holding the whole world up. I'm doing it. Yeah, no work. Awkward questions. Mythology and physics don't always work very well. So this question is thinking about rotational and translational motions. You know, I've talked about translational motion going somewhere. In the world of translational motion, you have velocity and velocity, acceleration, mass, forces, all that stuff. In the world of rotation, you have these other quantities: angular position, angular velocity I just showed you, angular acceleration when you twist something with a torque and cause it to change its angular velocity. That's angular acceleration. And the resistance to angular acceleration is rotational mass. It's the measure of the rotational inertia of the object. So that's fleshing out a little bit the 5 physical quantities of rotation. And so the question here is, if I throw a ball up spinning, so what's going on? If I throw it up spinning, it is sort of doing 2 things at once. It's talented here. It is undergoing translational motion in which it rises to peak height and descends. It's the movement of a falling ball. We did this already. Nothing new. At the same time, it was spinning steadily about a fixed axis in space while it was on its way up and down. I'm going to spin it so that it's got an angular velocity upward. There, I did it. And it went up and down the whole trip. It kept spinning spinning with an angular velocity that was upward. And nothing much changed to it. So far, we're okay with that idea? 2 things at once. When it reached peak height, it was momentarily motionless. Motionless meaning it had no velocity 0, and then it came down. But it wasn't not moving up there. It was spinning. It was still rotating. So how did that work? There is a Newton's first law of rotational motion, again on the lecture video, that observes that if you've got basically an object that's rotating, will continue to rotate as it was. It's inertia. It's a little messy because there are some words thrown into that Newton's first law that limit its applicability. It does not apply to objects that can change shape, so the objects have to be rigid. And it does not apply to objects that are wobbling. What's a wobbling object? This. Actually, I didn't throw that one wobbling. Let me get it wobbled. There it's wobbling. Where it's kind of going around a bunch of different. The rotational motion is very complicated. How to describe the complication? I'll come back to it because it involves rotational mass, which is a simplification. So if you neglect wobbling objects and you neglect objects that can change shape, like a diver that has just jumped off the 10-meter platform, the diver can change shape, and that means that Newton's first law doesn't apply to them. So we pick a rigid object that in this one can't wobble. It will continue to turn steadily about a fixed axis in space. In other words, its angular velocity, in the absence of any torques, any twists, its angular velocity is constant. Yeah?
Question about rotational mass. Is rotational mass the same as an object's regular mass? I know they're measured in different units, but are they technically the same?
Is an object's rotational mass the same as its regular mass? And the answer is no. They are related, but they're not the same thing. And furthermore, rotational mass is messy. And that's why I looked at this thing and talked about wobbling, and I decided, do I want to go there? I'm now going to go there. And here's the story. I can do it with this. Use them both. As background, I hope you're at least working with me if you've read or watched in the past that the 5 physical quantities of rotational motion, they're truly very analogous to the 5 quantities of translational motion with some subtleties added. So there's angular position, angular velocity, which is the rate at which angular position is changing with time, and angular acceleration, which is the rate at which angular velocity is changing with time. Okay? And angular acceleration is caused by torques, twists, the fancy name for twists. So you twist something, you're causing angular acceleration. So the ball's not turning, its angular velocity is 0. Twist, now the angular velocity is high. During the transition, while I was twisting, I caused angular acceleration. It's okay? The resistance to angular acceleration, an object's rotational inertia, how much it fights. It says, no, you can't get me spinning differently. That's the rotational mass. And there's an official name for it. Rotational mass, I'm not unique in calling it rotational mass, but there's an official name that many physicists feel absolutely, they're driven to use it. They have to do it. It's called moment of inertia. 3 words. It's a horrible name. It gives you no insight into what the thing is about. But it includes the whole story. And here's where the story gets messy. This ruler has an ordinary mass, which is how hard it is to make it undergo ordinary acceleration. Not too hard. Push it one way, back, forth. This one's easy to go from heading toward you, heading away from you. There's a lot of acceleration involved in that, and I can cause that acceleration with a fairly small force. Therefore, the mass is pretty small. So it's got mass. The rotational mass is the measure of how hard it is to make it change its angular velocity from, for example, this to this. So now I'm measuring rotational mass by seeing how hard it is to make it go back and forth like this from angular velocity. I mean, that one was angular velocity away from you. This is angular velocity away from you. It's a little hard to do. This here, that's angular velocity away from you. This is angular velocity toward you. And again, the directions for a physicist and an engineer, they're important. For you all, try to follow it. You may well never use it again in your life, but it's worth seeing some of this for a while. Okay? So this has got a certain amount of rotational mass. This is harder to cause angular acceleration than this one. That's easy. Okay? More rotational mass, less. We're okay so far? So here's the rub. Here's the stuff. First off, the rotational mass of this guy depends on which axis I spin it about. This has got a pretty big rotational mass. But if I spin it about this axis, ooh, that's easy. I'm still twisting it and still undergoing angular acceleration, but this is a lot easier than this. So this one object has 2 different rotational masses, depending on which axis you use. And actually, in principle, any object has 3. They have 3 different principal special rotational axes. Any object has 3 special rotational axes. Well, it's a little bit of an overstatement, but it's about right. And they will have 3 different rotational, they potentially have 3 different rotational masses about those 3 different special axes. It's hard to see all 3. This one, yeah, this has 3 very easily, well, it doesn't look like a tennis racket, but it's got a lot in common with the tennis racket. This is the face of the tennis racket. You can spin a tennis racket about its handle, and you can have the thin portion facing you or the wide portion facing you. So this is the face of the tennis racket. Now it's the side of the tennis racket. You okay with that? I wish I had a tennis racket, but I don't. Those three special faces, special arrangements, have 3 different rotational masses that are distinct. This is the easiest one to spin about, the handle axis. The next easiest one to spin about is this one. It's the frying pan face, where you're taking the frying pan and flipping. It's that face. And the biggest rotational mass is this one. There are 3 different rotational axes. I hope you can at least recognize that there are 3 different ways you can spin it that are sort of very fundamentally different. What's the point of this? And why are they different? First off, why are they different? It's because, let me go back to this stick. Rotational mass is not completely independent of mass. They're related. And an object's rotational mass, given how you're planning to spin it, so what axis you choose, the rotational mass depends on how far the ordinary mass is distributed away from the rotational axis. In this case, the rotational axis that I have in mind right now is pointing toward you guys, and a lot of the mass of the stick is far away from that. Is that okay? Therefore, that mass contributes a lot to the rotational mass of the stick. So objects that have a lot of their ordinary mass far from the pivot, from the center, from the rotation axis, have a lot of rotational mass. In contrast, now if I rotate it like this, the rotational axis is still towards you. And almost all the mass is right on that rotational axis. It's very close. The rotational axis is right there, and the mass is only in millimeters away. So it contributes very little to the rotational mass. So the rotational mass of this is very small. This is easy. All right? In this guy, because it's more complicated in shape and structure, this direction of rotation brings the ordinary mass as close as possible to the rotational axis. And therefore, this has the smallest rotational mass possible for this object. This rotation puts like that. It's kind of like, it's like throwing. That rotation axis puts the regular mass as far away from the rotational axis as possible. And this is the intermediate one. And it's hard for you necessarily to distinguish these two. It does lead to an interesting effect, and this is the kind of stuff that you end up calculating in first year of physics graduate school. You do the following kind of calculation. It is easy to throw this thing spinning about. It's the axis that gives it the smallest rotational mass. It is easy to throw this object so that it rotates about the axis that gives it the biggest rotational mass. It is well nigh impossible to throw it about the intermediate axis, the one that's got the medium rotational mass, the frying pan motion. So when you've got a tennis racket that you don't care if it hits the floor, try throwing it so it flips head over heels about where there's the face of the racket. You flip it like this, like a frying pan. It will tumble when you do that. It will wobble like crazy. You can't do it. You can't throw it so it flips smoothly about that axis. It will inevitably wobble into the other two motions. Is that important to you all? No, but it's kind of cute. Kind of cute. Try it. You'll see physics in action for whatever that's worth. Tori. Yeah. Why is it so hard? That motion is terribly unstable against wobbling effects. Any slight imperfection, if you throw it perfectly so it flips, it's so unfortunate I don't have a tennis racket. If you throw it perfectly so it flips like this, it will stay there. But any slight deviation will get worse and worse and worse with every flip until finally it's just tumbling wildly. It's got a name that is called the intermediate axis theorem, which you can go look up. You know, you can Google it and you'll find that it's an exponential growth away from that behavior, from that proper flip. Yeah? Is the rotational mass always measured from the middle? It actually matters, not necessarily. When you throw an object and let it spin on its own, which is typical, like this. It spins about a natural pivot. There's a point that stays put, that doesn't move anywhere. One special point in a ball like this, it's dead center in the middle of the ball. That should be sort of obvious to everybody. And it spins about that center. That center has a name. It's called the center of mass. It's an inertial thing. It's not called the center of gravity. The center of gravity is an other concept that I'll come to, or try to. But this point called the center of mass has nothing to do with gravity. It would be true in deep space. You know, take the astronauts out, whatever. They spin some object, a ball, and it spins about its dead center. That's the point about which all the mass, and therefore all the inertial stuff, is centered. In a ball, it's obvious whether it's going to be in the center. With this guy, not so clear. If I throw this guy, actually, I should say when I throw the ball, it's doing two things at once. It's traveling in the arc of a falling ball, but not all of it is traveling in that arc because it's doing funny, complicated rotations at the same time. The point that's doing the perfect arc of the falling ball is its center of mass. The center. So if I could have the center of mass there blinking as a blinking light, and that's the only thing you see, we turn off the lights and I threw this up, you wouldn't be able to tell it was rotating. You wouldn't be able, nothing about it. You just see this perfect, the dot, the center mass go, arc of a falling ball, life simple. At the same time, it would be spinning about its natural pivot, the center of mass, and doing interesting things. In this case, it would be following Newton's first law of rotational motion. It would be turning steadily about a fixed axis in space, basically at constant velocity. Is that okay? Yeah, klutz. Seesaw, okay, we did, topic done. If I throw this guy, its center of gravity was also, it's a mistake, center of mass. Center of mass, I wish I could excuse it as saying it's Friday, but it's only Wednesday. Maybe if there's cancellation of class on Friday, this is the effectively Friday. Okay. So I can, being adult, I can justify. Okay, so when I throw this thing and try to catch it, right? It looks a horrible motion, right? How do you describe it? It was traveling in the arc of a falling. Its center of mass, which is located about here. The center of mass was traveling in the arc of a falling ball while it was rotating about that center of mass. Its rotation might not follow. Might not have a constant velocity because this guy can wobble. It's unlike the ball. The ball can't wobble. This guy, because it's got several different ways in which it's got rotational mass and they can interact, you can have the wobbling problem. But, although we can't be sure it's going to be turning at constant velocity, despite having no torque on it, we can be sure that its center of mass will travel in the arc of a falling ball. Instead, if you want to find the center of mass of an object, you can throw it up and you can try to figure out from its crazy motion, but just support it so it can't fall and give it a spin. This guy, oops. You can see the point that stays put, and it's not going to matter how I get it started, although just for simplicity, I'm going to try to spin it. Give it a torque as close to what I think is going to be the center mass as I can. It's clear the center mass is somewhere near, or maybe even inside the head. All right? Actually, so rotational mass derives from ordinary mass, and the more the ordinary mass is far from whatever pivot you have in mind. Actually, the original question was, what if you force the pivot to be something other than the center of mass? For example, what if I make it pivot about my arm, my shoulder, like this? Now this is a lot of center. The center mass is in my shoulder. This is a huge rotational mass because a lot of the actual mass is very far from the pivot. So this is a lot harder to get going, start and stop, than this, or this is even easier. I'm bringing the pivot, and therefore the rotation center, closer and closer to the natural pivot. And finally, this is as low as I can go. Actually, this is as low as I can go. Okay? Long story, it's really messy. For fun, though, let me illustrate some of these effects with these two rods. So for this, I need two people to help me out here. Tori and Sam. Okay. So here's the idea. These both have mass, and actually they have the same mass. You can figure the same mass by shaking them, or you can just hold them up and see that they have very similar weights. So that's the first thing. Just see that convince yourself that they have the same mass, same weight. It's so good. You know, we're good, right? Okay. Now the issue is, I want Sam, you hold that one right in the center, which will be its center of mass. Well, it'll turn out, but and Tori, it's right in the center, which will also be. And when I say go, I want you to twist them back and forth as fast as you can. And in doing so, you're sort of measuring the rotational mass. How hard is it to make it go from one way to the other and back and forth? Okay? Ready? Get set? Go. So Tori is either incredibly strong, and Sam, or the opposite with Sam, or there's something different about these two rods. Okay? Trade. Try this again. Okay? Ready? Get set? Go. Hey, it moves. See, now Sam is the Amazon. Okay? So what's different? Where do you think the mass of this easy to twist back and forth rod is located? It's in your hand. So the tube, these are hollow tubes. All the mass is hidden inside where Sam is holding it. And Tori, where do you think the mass of yours is? On the ends. So the effect is dramatic. And you can't appreciate that. This is one of the ones, come up and try this after class. I mean, the fact that we're pinched for time a little at the end is annoying. But it turns out that the mass, you guys, thanks a lot. The contribution of each portion of mass to the rotational mass depends on the square of the distance of that mass from the pivot. So if you move it twice as far from the pivot, you quadruple its contribution to rotational mass. So it's a big effect. So the rotational masses of these two rods are different by a factor of like 20. It's a huge effect. Just because this class is supposed to be about real-world stuff, if you've seen tightrope walkers or seen pictures of them or cartoons of them, you see the person out there in their tutu walking along the rope with the stick, right? Okay? Why the long stick? It's got mass, but instead of having a mass like that, you could just hold a big chunk. You hold a brick. What's the difference? Mass, brick, same mass. By spreading the mass out on the stick like that, you've made an object that has a very large rotational mass. In fact, ideally, you put bricks on the end, so it's got huge rotational mass. Most of the mass is very far from the pivot. And then, when you begin to teeter, you the tightrope walker, you begin to teeter over to, away from you. I'm tipping, I need to be twisted back up. Well, how do I do that? I will twist the stick one way. It will twist back on me equally hard in the opposite direction. This is Newton's third law for rotation. So if I begin to rotate over like this, oh no, I'm in danger. I twist the stick hard that direction. In this case, it's away to your left. And it twists me to the right, and I come back up. Can you follow that idea? And because it's got a huge rotational mass, by virtue of being so long and having the mass far from the center, you barely see the stick move. Because even though I've exerted quite a large torque on it in order to get it to exert quite a large torque back on me, it undergoes very little angular acceleration because it's got a huge rotational mass. It hates to undergo angular acceleration. Okay? So there's physics doing something useful. Yeah. All right? Well, I should do seesaws before we get too far. Let me do this first too. This is also a question. Okay, this is also a good question. jar. Sitting on the table, to open a jar, you've learned your whole life which way to open a jar. Once in an incredible blue moon, you'll find a jar that opens backwards or something equivalent to a jar that will open backwards. But you know how to open a jar, right? Which way do you exert a torque on it? Is that what I asked? Yeah. Torque being a twist. What is the official direction of the twist you exert on a torque to open it? Okay? Questions about the question? Go for it. I'll give you till 30 seconds and we'll call it a day. Okay. Upward it is. Yes, indeed. Right-hand rule. So the rotation is clearly about a vertical axis. Which way? Thumbs up. Okay? So essentially all jars and things like jars are given what's called a right-hand thread. The right-hand thread agrees with the right-hand rule. Basically, you want the jar lid to move up. You want your thumb up. Turn it so the surface turns with your fingers. This is true of jars. It's also true of screw threads. Most of the screw threads in the world and bolts and stuff follow the same rule, the right-hand rule. The screw or bolt moves in the direction of the torque you exert on it, according to using the right-hand rule. All right? Get that out of there. Oh. It's another question worth asking. This leads up to the seesaw, and that is, I've talked about torques, which are the influence that causes angular acceleration. Torques are twists. But it turns out that torques and forces are not completely unrelated. So Mini-Me has brown hair. Mini-Me's been around a long time. And Mini-Me was made for a football television show in which I talked about how tackling, it matters where you tackle somebody. If you hit them high, hit them low, hit them at dead center, things behave differently. And that comes about because when you hit something, you exert a force on it. But that force can produce a torque. So forces and torques are related. It is possible to use a force to produce a torque and therefore to cause angular acceleration. And the question then is, if I want to make Mini-Me here undergo angular acceleration in the clockwise direction. Now the clockwise direction is a perfectly reasonable way of conveying to you which way I want the rotation to occur. It's going to be on an axis that points toward you and away from you, and in this case, clockwise is away from you. Same idea. I want to make Mini-Me begin rotating clockwise, or equivalently, I want to make it rotate in an official direction away from you. You okay with the idea? So which way do I want to push on Mini-Me? Which I will do with a mallet, that being the traditional influence here. We'll go to 20-ish seconds and then call it. 5, 4, 3, 2, 1, 0. B it is. Yeah, okay. More than 2/3 of you. Good. So the idea is this, that to make Mini-Me undergo angular acceleration clockwise, I could twist Mini-Me with my hand. Twist, okay, it worked. Or I can push on Mini-Me in various places. The big mallet. And the push will produce a torque. And the ways that will not work, let me get this out of here so I can see. If I try the top of his head towards his feet, I mean, other than getting a concussion, this is not very effective. the side of his head toward the right. Well, this is the winner, right? Boosh, that worked. The other ones that don't work are the middle of his body doesn't help, and the side of his feet toward your right spins the wrong way. And actually, this is where this was relevant in football. If you tackle somebody high, you hit him here, you cause them to rotate, in this case, away from you. If you hit them low, it causes them to rotate, in this case, toward you. If you hit them dead center, no rotation. And that comes about because these forces are producing torques. And the rule for where do they come from is you cannot produce a torque on something by pushing it either at the center of rotation or toward the center of rotation or even away from the center of rotation. That produces no torque. But you can produce torques on something by going away from the center of rotation and pushing at least partly at right angles to your displacement from the center of rotation. So here I've gone to the top of mini-me, which is an upward shift, has a direction to it, and push not upward or downward, which is along that displacement, but at right angles to the displacement, like to the right. That works. And where this distills down to is this displacement from the pivot to the point where you're going to push is called the lever arm. And this is the world of levers. This shows up everywhere in lever stuff. So whether this is a lever you use to tighten or loosen nuts and bolts on some piece of equipment, or it's your lacrosse stick or field hockey stick, when you get away from the pivot, and now you want to, so that displacement is called the lever arm, and it has a direction. Officially, it's a vector. And you push at right angles, or partly at right angles, to that vector with a force, you produce a torque. And the torque is it's equal to the lever arm times the force, assuming perfect right angles. So the harder you push and the farther you are from the pivot, the more torque you produce. So that's the case here. My example in the book, and one that I like, is opening and closing doors. Most doors, the rotating kind, they rotate about their hinges. How do you open or close one of those doors? An act which requires angular acceleration of the door, because it's sitting there it's sitting there closed and motionless. And then you want to get it to open. You want it to undergo angular acceleration to open it. You go away from the pivot. Don't push at the hinges. You've surely done this sometime in your life. You've tried to open a door by pushing it at the hinges. All you do is break your hand or your face or whatever you use to push with. So go away from the hinges, get yourself a lever arm to work with, and don't push toward or away from the hinges. Get the doorknob now. It's far from the hinges. This is a good place to start, but don't push the doorknob toward the hinges or away from the hinges. That doesn't produce torque. Go at right angles to that vector, and now you open and close the door. All right? On a seesaw, the kid, to produce a torque on the seesaw, so I would say something about seesaws before the time gets completely away from me. The kid, don't put the kid on the pivot. No torque. Take the kid away from the pivot and let the kid push. And when that happens, torque. All right? And the torque is the product of how far you went away, that's the length of the lever arm, times how hard the kid pushed, which is related to the kid's weight. So if you got two kids of equal weight, this kid produced a torque, and the torque turns out to be away from you. This kid produces a torque, and the torque happens to be toward you, and they're now exerting equal but opposite torques on that bar, and they cancel each other's torques. So there's no net torque on it. That's too brief, too terse. So we'll get into it either on Friday or if we're underwater on Monday. All right.